Today I'm going to be doing example 8 out of the PDF, which is also chapter 29, example 4. Let's see. Example 29.4 out of the textbook. What we got in this problem is a semicircle cut piece of wire, kind of like this. And we have an electric current moving through it this way and this way. And then we have electric field moving up all throughout this. We'll label this B for the electric field. We'll also label our X and Y axis here. Y, X. So what ends up happening here is we have two different forces for this piece of cut wire. So we want to find the force along this straight piece. We'll label this F1B. And we want to find it in relation to the electric field, because that is also having an effect on it. And then we'll label this piece right here F2B. So let's start with F1B right down here. And we'll look at our basic equation for length in relation to current in the electric field, which is current times the length cross B, the electric field. So what ends up happening is you differentiate this equation, so it becomes D F1B times the current DS cross B. Now DS is a infinitesimal cut piece of this wire, and the force that's coming off of it. So through F1, we're looking at the x-axis here. So you could think of this being as ds, and it kind of moves in this sort of way along the wire. And when it comes all the way down to F1 here, every part of it is sticking up. So because every part of it is sticking up, we can, along the x-axis, we can create a little equation here, ds is equal to dx, and just substitute that in. So dF1B becomes the current times dx cross B. B is in the I. This is the I, and this is the J. We'll just cross out X and Y there. Cross B times I, J. And with the right-hand rule, you have I going this way, and it moves towards J, so it's pointing up. So this becomes B, K, just like that. And then, if we have our radius here, I'll go ahead and label this our radius. Our radius is the same down here too. This is also R. So what we're going to want to do is differentiate F1 here from minus R to R of the current times electric field times dx k. Oh, sorry, this is supposed to be dx right here. Okay. So we can pull I and B out of this. So it really just becomes IB times X minus R to R, which becomes IB to R K hat. So we know the force on this first part of the length is equal to 2 I R B K hat. That's 2 times the current times the radius times the electric field in the upwards K direction. All right, now let's take a look at F2, our current along this path. F2 is also equal to the current times the length cross B. So what we're going to do is differentiate that again, just like we did last time. df2b is equal to I ds cross B. But now, because we are working not in just the I and the j axis, we have angle theta here. It's going to become B theta cross j, which, if we do a little equation over here like we did up here last time, our ds is going to be equal to the radius right here times d theta. D theta is this little infinitesimal cut of ds in relation to that. So ds is going to be equal to r d theta. So we can change up this equation even more and make this I r d theta times b theta cross j hat. Alrighty. Let's see here. Okay, then what we're going to need to do is substitute in for theta right here. So theta, just so we can differentiate, theta is going to be equal to, we'll just reorganize this a little bit, cosine theta j hat minus sine theta I hat. And those are just like your x and y coordinate. Now since we're working in sort of spherical terms, those are your x and y coordinates. And we'll cross that by j hat. So once you simplify this, it's going to be equal to negative I r. Here, let me do this. Negative I r b sine theta d theta in the k hat direction, because it's also going this way, or it's negative because it's going, it's going this way, but the electric field is curving that way, so it'll be pointing down because it's bending that way. Yeah. So then what we do is we differentiate this from 0 all the way to pi, since it's a semicircle. From 0 to pi minus I r b sine theta d theta in the k hat direction. We'll take negative I r b outside this equation. Just becomes sine theta d theta. And of course, sine theta, when differentiated, becomes negative cosine theta from 0 to pi in the k hat direction. This becomes cosine pi minus cosine 0. Oop. Didn't mean for that to be theta. Cosine 0 k hat. Cosine pi is equal to minus 1 minus cosine 0, which is equal to 1. So this becomes a minus 2. Multiply it by this minus over here. Comes 2 I. Oh wait, I messed that up. This should be a minus cosine theta. So what we can do actually is just take this minus outside the equation, have it cancel with that minus, so that becomes a plus. So that should just be a plus over here. And then there's no minus over here anymore. So this is minus 2 times IRB minus 2 IRB k hat. Thank you for watching this problem. I'm not great at making videos, but here you go.